Hello, ladies and gentlemen. Welcome back to Lesson 2.2, Day 2 notes. We are still in Unit 2B, and we are looking at least squares regression lines, residuals, and residual plots. All right, so what is the general form of a regression equation? And what is the difference between y and y hat? So this symbol above the y is the hat symbol. All right. If it's written a little bit larger, it looks like this, and we identify that as y hat. Now the equation would be y hat equals a plus b times x, where a is the y-intercept and b is the slope of the regression line. Now y represents the actual value of y that we would get from gathering data. Y hat is the predicted value of y based on a value of x. So if we were to put a number for x into our equation and calculate y hat, that would be our prediction. The y coordinates of the points actually on the graph are the actual y values that were gathered from data. Now, what is extrapolation, and is it a good idea to extrapolate? All right, so for our definition, extrapolation is the use of a regression line for prediction outside of the interval of x values used to obtain the line. The further we extrapolate, the less reliable the predictions. All right, so there's a caution here. Few relationships are linear for all values of the explanatory variable. Don't make predictions using values of x that are much larger or much smaller than those that actually appear in your data. So you have to be very careful. Don't extrapolate too far. All right, let's take a look at example 1. How much candy can you grab? All right. We did the candy grab activity on our first day as our introductory activity. This is another class's candy grab activity. So the scatter plot shows the hand span in centimeters and the number of starburst candies grabbed by each student when Mr. Tyson's class did the candy grab activity. The regression line, y hat equals negative 29.8 plus 2.83x, has been added to the scatter plot. So we have the scatter plot here. We have our regression line already included. All right, for letter A, Andres has a hand span of 22 centimeters. That would be our x value. Predict the number of starburst candies he can grab. It's asking you to calculate y hat. All right, so use your equation for y hat and put the value of x in place of x. So I'm putting 22 in place of x. And if I go ahead and type all of this into the calculator, I would have negative 29.8 plus 2.83 times 22. And that gives me 32.46. So we would predict that he would be able to grab approximately 32.46 starburst candies. Now I know that you can't actually grab a partial starburst candy, but this is just our prediction. We're going to go ahead and include the decimals for this. Now for letter B, Mr. Tyson's young daughter, Michaela, has a hand span of 12 centimeters. Predict the number of starburst candies she can grab. So 12 is now our x value, and we want to predict y hat. So again, put 12 in place of x and calculate this out. So if I type in negative 29.8 plus 2.83 times 12, this time I only get 4.16. So we're predicting that she would be able to grab 4.16 starburst candies. Now, how confident are we in each of these predictions, and explain? Now, the prediction for Andres is pretty believable because 22 is actually within the data that was gathered. So 22 is within the interval of x values that was used to create the model. It was within the data set. So that prediction is pretty believable. The prediction for Michaela is not as trustworthy because x equals 12 is really far outside of the x values. The smallest x value that we had was 17 centimeters. 12 is 5 centimeters smaller than that. All right, so it's far outside the x values used for the regression line, and the linear form may not extend to hand spans that are this small. All right, it would be better for us to go ahead and do the activity with Michaela's class so that we have other students who have potentially similar hand spans, or at least of a similar age, and create a new scatter plot based on her class. Younger children also have different grip strengths and different fine motor skills. So they may or may not be able to grab as many, even with similar size hand spans, as an adult would. right? We were doing this activity with seniors, right? You guys are basically either in early adulthood or on the cusp of it, which means that your grip and fine motor skills are very different from a young child. All right, so this is kind of an illustration of the caution about extrapolation and making predictions. Now, let's talk about how we can assess how good a prediction actually is. So what is a residual and how do you interpret a residual? So our definition is that a residual is a difference between the actual value of y and the value of y that's predicted by our regression line. So another way of saying that is that the residual is equal to the actual y minus the predicted y. So it's y minus y hat. And this is one of the topics covered in AP statistics. So one of the ways that we remember that there is that they're in AP. So A comes first, P comes second for actual minus predicted. You could actually just remember this in alphabetical order. A before P, actual before predicted. Or original symbol minus adjusted y value. Now, for a content connection, all right, think back to finding standardized test scores, in other words, our z-scores. All right, we would start by calculating the difference between the observed value and the expected value, the mean. All right, we're still doing that. The actual y value is the observed y value from the real-life data point. The predicted y value is the value that we would expect y to take for that same value of x using the model equation. And so the interpretation of this is that the actual, whatever your y value happens to be, is however much your residual is, more or less, depending on whether you had a larger actual or a smaller actual compared to your prediction. So it's either more or less than the value predicted by the regression line using x equals whatever you set your x variable to be. Because our regression lines are dependent on what we assign as our explanatory variable versus our response variable, and those aren't always clear. We have to identify what we use as our explanatory variable, our x variable, when we're making our interpretation. All right, let's take a look at the next page. All right, so we have another example here. And example 2 is, can you grab more than expected? All right, so we're still looking at that candy grab activity. So here again is a scatter plot showing the hand span in centimeters and the number of Starburst candies grabbed by each student in Mr. Tyson's class. All right, the regression line is still the same as we were using before. Now we need to find and interpret the residual for Andres, who had a hand span of 22 centimeters and grabbed 36 Starburst candies. So we had already previously calculated his predicted number of Starbursts. And that's what I'm doing here at the top. So first, if you're asked to do this question and you're not asked to actually find that value first, then you need to find the prediction for how many Starbursts we think he could grab. All right, we know how many he grabbed, but what does our prediction line say? So put 22, which is our x value, in place of the x in our equation. Go ahead and calculate this out. I showed you that previously. And we had gotten 32.46 Starbursts. Now the residual, notice that I'm writing out the word in full. You can either abbreviate this as RESID for resid, or you can write out the word. Please do not use the letter R. In a future lesson, you're gonna find out, or actually in our previous lesson, you guys found out what R actually represents. It was our correlation coefficient. Because the residual is different from the correlation coefficient, you can't use the letter for the correlation coefficient as an abbreviation for residual. That's why this one gets written out. So residual equals our actual y value. He actually grabbed 36 Starburst candies. So that's our actual y value, minus the predicted y value that we just calculated. So how many he actually grabbed minus how many we predicted he would grab. So 36 minus 32.46 gives you 3.54 Starbursts. Now the interpretation for this is that Andres grabbed 3.54 more Starbursts than the number predicted by the regression line with x equals handspan. All right, so I'm using the sentence frame that I gave you on the previous page to write this interpretation. Now, how do you interpret the slope and y-intercept of the regression line? All right, for slope, we say that the predicted, in this case, it would be number of Starburst candies grabbed, goes either up or down by about however much our slope is for each increase of 1. Use your units for your x value. in and then actually identify your x value in context. So the predicted y value goes up or down by whatever the slope is for each increase of 1. Put your units, in this case centimeters, from the handspan in and then identify your x variable. Y-intercept is the predicted y value is about, and then identify what your y-intercept was when identify your x variable in context is 0. All right, I'll show you these here in the next example. Now, note that these are called the estimates of the parameters of the regression line. They're not the actual parameters. All right, so we're still doing estimates here. Now, for example 3, grabbing more candy. All right, so we're still going on with that same example. So we had our scatter plot, and we had our regression equation, and we need to interpret the slope of the regression line. So let's go ahead and use the sentence frame. So the predicted number of starbursts grabbed, right, that's my y variable in context, goes up by 2.83 for each increase of 1 centimeter in handspan. So the predicted number of starbursts grabbed goes up by 2.83 for each increase of 1 centimeter in handspan. Notice that I am not rounding this number. I didn't round it up to 3. You need to keep the decimals in this. These are estimates. If you go too crazy on the rounding, then your predictions are going to be really, really off. All right, now for letter B, does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept, and if not, explain why. All right, so in this case, I want you to think about what having an x value of 0 would actually mean. So an x value of 0 means that you have a handspan of 0 centimeters. That pretty much means that either your hand is stuck closed or you don't have a hand. Either way, are you grabbing things if your hand is frozen closed or you don't have a hand to begin with? This is why we're going to say that the y-intercept does not have meaning in this context, because it's impossible to have a handspan of 0 centimeters and actually complete the activity. And when you take a look at this, it's not even possible to grab negative candies. So saying that a student with a handspan of 0 centimeters would grab negative 29.8 starbursts, that sentence just doesn't make sense. So with y-intercepts, because it's often an extrapolation that is really outside of the data that was gathered, we very rarely interpret these. Sometimes we do, if we've adjusted our x values to represent to basically start at 0 for the data set that we gathered, then we can interpret the y-intercept. You'll come across this once we get to our summative project. Now, what's the most common error that students make when interpreting slope or in the y-intercept? And that would actually be forgetting to include non-deterministic language such as predicted. Notice I'm saying the predicted number of starbursts grabbed goes up by 2.83. I never said the actual number. If you leave off the word predicted or leave off like the word estimated, then you're implying that the actual number of candies that people grab increases by this for 1 centimeter increase in handspan. And that's not actually an accurate interpretation of what that line is supposed to tell you. That line is made up of predictions. So you have to refer to the fact that they're predictions. All right, let's go to our next page. So how can we determine the best regression line for a set of data? And what name does it have? All right, so for the definition on this, the least squares regression line is the line that makes the sum of the squared residuals as small as possible. It's why it's called the least squares. And it's called a regression line because regression is actually going backwards from all of the data that you have and calculating the specific parameters that you need to be able to represent that data. So it's a way of working backwards. Now your calculator or a package of statistical software will give the equation of the least squares regression line from data that you enter. Then you can concentrate on understanding and using the regression line. There is no firm rule on how many decimal places to provide when rounding. Round based on the context of the problem that you're working on. So if you're dealing with money, go out to 2 decimal places because money is in terms of dollars and cents. Right? Now, how do we use your calculator to find the equation of the least squares regression line? Well, first, you are going to go to Stat, and you are going to hit Enter on Edit and actually enter some data. All right, now I have a data set on this next page down towards the bottom that I'm actually going to use for this. So I'm going to go ahead and type this data in to show you these steps. So 2521, 2555, 52846, 3028, 3049, 3198, and 3198. And I have 400, 426, 428, 435, 469, 475, 488, and 455. All right, so with this data set, I'm going to go ahead and work through this now. Let me get this back in focus. There we go. All right, so once you have data entered into here, go to Stat. I'm going to hit the Stat button. Go over to Calc, so hit the right arrow. And we need to choose a regression type. Now, it's not necessarily starting at 3. Let's see. Least square regression line can either be used with number 4 or number 8. Now, you guys are actually used to seeing this in terms of slope times x plus y-intercept instead of the other way around. The way that I was talking about it earlier was actually number 8. That's the way that we tend to look at in statistics as opposed to in algebra. It's okay whichever one you use, just keep track of which letter should go with your x and which one is your y-intercept. So I'm going to actually go with number 4, which is linear regression the algebraic way. And I'm going to hit Enter, and it asks you for your X list. So usually we have list 1. Now, if your list is missing or if you have the wrong list there, notice that the list numbers are above the number keys in blue. So if I want to use list 1, I need to hit second 1, and then Y list is list 2, store my regression equation, and I want to store it as Y1. All right, frequency list is usually left blank. Let's see. I want to store this in the Y equals. Now this says to use alpha, trace, and then F4. So if I use, let's see, alpha, and then the trace button has the 4th function menu, and this has the list of all of the Y1 through Y sub 0 options for the Y equal screen. So hit Enter on option 1, and then go down to calculate. And this just came up with my my slope, my y-intercept, r squared, which you'll learn about soon, and my correlation coefficient. So this has a very strong correlation coefficient, but until we look at a graph, we can't really trust that correlation coefficient yet. All right, so we have our regression, and if we want to calculate r and r squared, now mine's already showing up, but you have to make sure that, let's see, this one's giving slightly different directions than I usually do. I tend to just go to mode, and I scroll all the way down towards the bottom. Just make sure your stat diagnostics are on. Mostly they get turned on, but if you've reset a calculator recently, those diagnostics get turned off. So I would say before you start calculating, just make sure that those diagnostics are on. All right, to turn them on, if it says off, arrow to the right, hit Enter on, and then quit out of that, and you have your diagnostics. Now, if you've already gone through and tried to calculate your equation and then had to go back and fix it so that your diagnostics were on, if you arrow up, you can select the command that you had given the calculator previously, and it will go through and recalculate, and it'll actually show r squared and r. If those stat diagnostics are off, then r squared and r will not be there. All right. Now, if you want to be able to see your graph, I'm going to show you this real quick. I don't think I have this on here, but if you want to be able to see the graph, hit second and then y equals, and hit Enter on that very first stat plot. Make sure it's on. You want to use the first type of graph, which is a scatter plot. Y list is list 1, X list is list 1. Y list I'm going to change to list 2. So I'm going to hit second and then 2 to activate that blue L2. Hit enter and then go to zoom, and zoom stat is option 9. So you can see my scatter plot and you can see the line of best fit going through it. All right, now, what is a residual plot and what is the purpose of a residual plot? So residuals are those vertical distances between your actual y-coordinate and the predicted y-coordinate. So the further the vertical distance between your point and your regression line, the further off your predictions actually are, and the larger your residual, either in the positive or negative direction. Now, for a residual plot, we take all of those residuals for all those different values of x, and a residual plot is a scatter plot that displays all of those residuals on the vertical axis and the explanatory variable on the horizontal axis. And the purpose of the residual plot is to help us assess whether or not a linear model is appropriate. It also helps us with other kinds of models. Now, an example is over at the right here. So figure 3.10a shows the scatter plot representing the relationship between the average income, gross domestic product per person in dollars, and fertility rate, number of children per woman, in 187 countries, along with the least squares regression line. All right, so that's what this graph is showing. Now, this looks pretty curved to me. I'm not sure that a line would really be best, but let's double check it. So the residual plot in figure 3.10b shows the average income for each country and the corresponding residuals. So you still have average income along the x-axis, but now we have the residual along the side for each of these individual points. Now, if you notice, the least squares regression line clearly doesn't fit the association very well. There's a U-shape in the pattern, U-shaped pattern in the residual plot. So there's this U-shape right here that indicates that a linear form of our model doesn't match the form of the association. A curved model might be better in this case. Now in figure 3.11a, the scatter plot shows the Ford F-150 data along with the least squares regression line. So you have miles driven, and then you have the price of the vehicle. And as you can see, the points are kind of scattering above and below this line as you're going from left to right. I would say that a linear model might actually be appropriate for this one, but the residual plot kind of puts under a microscope. And the corresponding residual plot is shown in figure B over here on the side. Now, the thing that I want you to notice is that while there seems to be a potential linear pattern in the scatter plot, the residual plot shows no obvious pattern. What that means is that when we actually graph that line and then we start taking a look at the vertical distance between the points in the line itself, there's no additional pattern present in those points that wasn't accounted for by the linear model. All right, so looking at the scatter plot, the line seems to be a good fit for this relationship, so you can see that the line is appropriate by the lack of leftover curved pattern in the residual plot. If there's a different pattern that's better for the scatter plot, it'll show up as a pattern in the residual plot. So if there is no pattern in the residual plot, that means that the model that you're using is actually appropriate because it used up all the pattern in how it was relating to the points when it was drawn in. All right, so the residuals look randomly scattered around the residual equals 0 line. That's the hallmark of a good fit. And once again, we need to actually visualize that fit because we try to visualize what kind of model would be most appropriate by looking at the scatter plot to start with. So we verify that our model is appropriate visually as well with that residual plot. This is not optional. You actually need the residual plot to be able to double check the fit. All right, so what do we look for in a residual plot? Let's kind of formalize this. How can you tell if a linear model is appropriate? So what we look for are leftover patterns. So the form of the residual plot equals the form of the association minus the form of the model. So if there's a leftover curve pattern, the form of the model wasn't appropriate. No leftover curve pattern, form of the model was appropriate. Also consider the size of the residuals to get a sense of the typical prediction error. If those residuals are really large, then your predictions are going to be pretty far off, so you might not want to make predictions using a model in that scenario. You cannot use the correlation coefficient to assess linearity. It only reveals strength and direction, not the form, which means that you have to look at the graph to see whether or not a linear curve model is most appropriate, and you have to verify it with that residual plot. All right, so when asked if a linear model is appropriate, students will sometimes incorrectly use that correlation coefficient to justify linearity, but a strong correlation doesn't mean an association is linear. An association can be clearly nonlinear and have a correlation close to positive or negative 1. And only the residual plot can adequately address whether a line is an appropriate model for the data, showing the pattern of deviations from the line. So we have an example off to the side here. So this is graphing the function y equals x squared for integers from 1 to 10. And the line here actually yields a correlation of 0.97. So that would be considered a very strong linear relationship. However, this is half of a parabola. We shouldn't be using a linear relationship. And it might be harder to see initially, but when you actually look at the residual plot, that parabolic relationship is extremely obvious. It literally looks like a parabola in the residual plot. So the vertical distance between each of these points and the line is shown here, and this shows the pattern that should have been used to begin with. Now, how do you make a residual plot using your calculator? Because I don't expect you to calculate all of your residuals by hand and go through and actually come up with your residual plot by hand. That's just a little bit too much work. So we previously looked at how to find our scatter plot with our line in there. Now let's take a look at how to get the residual plot. So first, just make sure that you have your data entered into list 1 and list 2, all right? And run the linear regression command, which I already did. Then press second y equals and hit enter on that first plot. And we want to make sure it's on. Make sure we're using the scatter plot. And for our y list, instead of leaving it as list 2 where the y values are, press second and then the stat button. We want to go to all of our lists. So second stat takes us to the list that we can use, and we want to use the residuals. So we're going to go all the way down to number 8. And then press zoom 9 in order to restructure your graph according to the plot that we're using now. So zoom and then 9. And now you can actually see your residual plot. See how this matches what's on the paper? So let's take a look at our final example, and we're dealing with a tennis player. So our taller tennis player is able to serve faster. Physics would suggest that this is the case as taller players have longer arms and can generate more racket speed. The table shows x equals height in inches and y equals average first serve speed in miles per hour for 16 professional male tennis players. So let's take a look at this. Now, when you need to clear out data like this, go up to the very top, hit the clear button because I want to clear it out, then hit enter, and that actually clears out the data. And then you're ready to type in new data. So we have 75, 78, 76, 78, 77. It's important to get these in the same order that they're written in on the paper so that our x and y coordinates stay matched. 75, 73, 71. And then over here, I have 108, 122, 113, 3, 120, 118, 128, 116, 106, 124, 119, 125, 110. There we go. All right, so calculate the equation of the least squares regression line. So to calculate that, I'm going to go to stat, I'm going to go over to calculate, I'm going to go down to option 4, linear regression. I'm going to store my regression equation. So I'm going to hit alpha and then trace to get that F4 menu. Hit enter on number 1, and now it's going to store my equation in Y1 so I can get my residuals list. Calculate. And A is my slope, B is my y-intercept. I'm going to go out to about 2 decimal places. So I have y hat equals 1.41x plus 12.05. That's my equation, my least squares regression line. Now to get this kind of a graph, go to my stat plot, hit enter, go down to list 2. So make my y-list list 2, zoom stat, so option 9. And you can see my scatter plot here with the line drawn through it. I use a different computer program that I can show you guys in class to get this one, so that was nicely scaled, but you can actually see it here as well. Now this looks like it should probably be linear, so linear equation probably is appropriate, but we need to double check it with the residual plot. Make sure there's no pattern that we're just not able to see with the naked eye. So this is kind of like putting it under a microscope. So make a residual plot for the linear model of the data. Now for that, you don't have to scale it as nicely as I have it here. Again, I did this with a program. You can just do a sketch. And for that, alpha y equals, not alpha y equals, my bad. I want to hit second, clear that out, second, y equals to get to stat plot. Every now and then I get my buttons mixed up too. Go down and instead of my y list, I want to replace it. So I'm going to hit second stat to get to lists, and again, go down to that residuals list. And now I can hit zoom 9 in order to get my residual plot. And the residual equals 0 line would represent points that are exactly on the least square regression line. The further the points are from that x-axis now, the larger or more negative their residuals are. So the further off the predictions are from reality. So this shows you the prediction errors at these various points. Now, since this seems to be pretty scattered around the residual equals 0 line, there's no obvious pattern. That means that the residual plot indicates that a linear model is appropriate. So linear model is appropriate because the residuals are evenly scattered around the residual equals 0 line. All right, that's the end of our notes. I'll see you in class.